Okay, hi guys, so we'll be continuing on seeing effect of various other influences on the equivalent constant or equilibrium constant. So before starting on, let me take from the previous lecture that if someone might not have understood, I will repeat what we discussed in the last portions of the previous lecture. So before going into that, let's first see what is Kc. So Kc is nothing but concentration of, let's say, product C, product D upon, which is the products divided by concentration of reactants. So if we look at it closely, we can see that concentration of C can be written as moles of C. This is raised to the power respective stoichiometric coefficients. So moles of C divided by volume of solution, which is V raised to the power C. Again, for D as well, I can write the same thing. For A as well, I can write the same thing. And A, this is capital A. Upon V. Similarly for B. So simplifying this, we will get Nc to the power C and D to the power D and A to the power A and B to the power B multiplied with 1 upon V to the power delta Ng. Delta Ng is nothing but B, C plus D minus A plus B. So this is the form we get of Kc. Similarly for Kp, we can write that this is partial pressure of C to the power C. Similarly for all other molecules or compounds present in the mixture. So partial pressure of C would be nothing but, we can write it as moles of C divided by total moles, which I am writing T. Similarly moles of D, which is the mole fraction of D raised to the power D, into, obviously I will write total pressure into the raised to the power C into total pressure raised to the power D. Similarly total pressure raised to the power A, moles of A divided by total moles, which is mole fraction of A, and moles of B divided by total moles and total pressure of mixture. So we can write it as Nc to the power C into Nd to the power D divided by Na to the power A and Nb to the power B multiplied with P upon total moles at equilibrium raised to the power delta Ng. So please remember these two forms in calculating the effect of any other external agency over the reaction, or specifically the reaction equilibrium. So when I say from the last lecture that in the addition of inert gas, which you were seeing in the last lecture, in the addition of inert gas portion, now according to this formula, what will happen if we have a constant volume, means we add the inert gas at constant volume. So in Kc, if we see that volume is constant, hence Kc would not be changing, hence there would be no effect. Okay, and in Kp, if we look, then P of overall mixture at equilibrium, P at equilibrium, or directly I am writing P multiplied with V equals to total moles, which is N, R and T. Okay, now as we are keeping the volume pressure constant, in the second case when I am keeping the pressure constant, as I am increasing the total moles, what will happen? The P by total moles terms, which is nothing but this term, P by total moles term, will actually decrease as total moles are increasing at constant pressure, hence P by T ratio will decrease. Now if delta Ng is equals to 0, then there will be no effect on equilibrium, but if delta Ng is positive, then Qp, or Qp, which is the state of the constant at any point of time. Okay, so the Qp will be again this term or this formula. The Qp would actually decrease, so in a sense Qp will go lesser than Kp. I am writing it here only. So if the second case was delta Ng is positive and we are increasing, pressure is constant and we are adding inert gas. So what will happen is P by T ratio will decrease. This implies Qp would become less than Kp. What happens when Qp becomes less than Kp? Equilibrium shifts towards forward direction. Equilibrium shifts towards forward direction. Now as equilibrium shifts towards forward direction, what we can say more about it, that it will shift towards more of the product formation. Okay, then what will happen? What else can we say? As delta Ng is positive, this implies moles of C plus D in totality would be more than moles of A plus B, or the reactants, or the stoichiometric coefficients of products would be more than stoichiometric coefficients of reactants. That implies more number of moles would be formed. So reaction is shifting towards more number of moles formation. So simply put, if I take some example, that let's say A gives 2 moles of B, A gaseous gives 2 moles of B gaseous. So what will happen is, if reaction is shifting towards forward direction, then I am losing 1 mole but I am getting 2 moles of B. Hence more number of mole formation is taking place when pressure is constant and delta Ng is positive. Okay. Now what else can we what else case can we have when delta Ng is negative? Now when delta Ng is negative, we are adding more pressure, means more moles, as pressure is constant. Hence P by T ratio would also increase only in this case. T is not temperature, T is total moles. Okay. So as number of moles are increasing, P by T total moles ratio is not increasing, this is decreasing rather. Now as P by T moles ratio is decreasing, what will happen to Kp? So as this is decreasing and this is delta Ng is negative, so it would have the reverse effect from the previous case, in a sense that Qp would become more than or larger than Kp. So this implies reaction will shift in backward direction. Now as the reaction is shifting in backward direction, what can we say, that the products will be again forming, or rather going into the backward direction and forming reactants. Okay, so in this case products reactants formation would be there, as we have already written. So this is implicit from the previous line, but I'm writing it again. So what will happen now is, obviously, if this is the reaction what we are talking about, from B, the gaseous product A formation will take place as the reaction is shifting in backward direction and delta Ng is negative. This implies stoichiometric coefficients of reactants is more than stoichiometric coefficients of products. Hence, if 1 mole of B is uh, going backward to form 2 moles of B, again more number of moles formation will take place. Okay, so in a note, simply I can write from concluding from the both cases, that whenever we add inert gas at constant pressure, equilibrium shifts towards more number of moles. Okay, whenever we add inert gas, equilibrium shifts towards more number of moles. Okay, so now let's see what is the effect of temperature on the equilibrium constant, or the direction of equilibrium. So increase in temperature favors endothermic reaction. This is the point we have already seen. Favors endothermic reaction. And next, decrease in pressure or rather temperature. Decrease in temperature favors exothermic reaction. Okay, so let's say we have a equation where on providing heat A dissociates into B plus C, and B plus C actually would on releasing heat will convert into A. So we can say that in the forward direction it's a exothermic process or endothermic process, and in the backward direction it's a exothermic process. So for exothermic reactions we can say that let's see first for endothermic reactions. So for endothermic reactions we can say that temperature increases, equilibrium shifts in forward direction, and if temperature decreases, equilibrium shifts in backward direction. Okay, now for exothermic reaction we can say the same. So for exothermic reactions we can say that as temperature increases, equilibrium shifts in backward direction. And why is this the case? Because the nature of the reaction is such that it will release heat and form products. Now if we are increasing the temperature, less number of reactants would favor to go or convert themselves into products, or in other terms, products in turn would go and form reactants. Because for the formation of products, heat release is required, but as we are increasing the heat or giving more heat, less number of reactants would go convert into products, and or in other terms we can say that products formed previously would also, after the increase in temperature or providing the heat, will convert themselves back into reactants. And as the temperature just decreases or we are taking away the heat from the reaction mixture, equilibrium shifts in forward direction. So this is the ideal condition for exothermic reaction, because exothermic reaction itself wants to release the energy, and if we are not providing any energy or taking the energy away from the system, the reaction will actually go into the forward direction in order to convert more products, and side by side also create more energy in the system or release more energy in the reaction mixture. Okay, so with this we come to the end of this lecture. In the next lecture we will be seeing simultaneous equilibrium. So till then, good luck and goodbye.